So I talked about climate science before the break. I gave a hint at some scenarios. I'm going to talk a little bit more about the scenarios as well as where do these greenhouse gas emissions actually come from. It should be obvious to you that if fast climate change is driven by this complex of factors, a range of greenhouse gases, aerosol emissions, land use change, that was true in the past. There's no reason to assume that the future will be any simpler, right? So we would, to build a proper scenario, we would need to understand all these things. But each of these components in itself is actually complex. What you're looking at here is the global emissions of greenhouse gases in the year 2005, split by gas. So we see methane capturing about 20%, nitrogen capturing about 8%, the industrial gases about 1 or 2%, and then the rest is CO2. But CO2 in itself is also fairly complex in the sense that it has a range of sources. The biggest one is the CO2 emitted from the production of electricity, generation of electricity, and a bit of heat, but it's mostly electricity, about 32%, followed by transport emissions of about 15%, manufacturing emissions of about 40%, and residential of about 8%. So CO2 in itself also has a range of approximate causes. Don't walk away from this picture saying it's industry that did it. It's those bloody utilities that are producing all that CO2. That's not why they're in business, right? They're in business to make electricity that we use to project slides, that we use to load up our phones, that we use to watch telly or whatever you do with electricity, right? They don't do it for themselves. They do it so that they can make electricity to sell to us. Those 8% residential that you see are the emissions directly from our houses, mostly for heating, a little bit for cooking. So where does all this stuff come from in terms of processes and sectors? Carbon dioxide, as you know by now, is the most important anthropogenic greenhouse gas. The most important thing there is the combustion of fossil fuels. Not all fossil fuels are created equally. If you burn gas, you emit about 57 tons of CO2 per terajoule of energy gained. Whereas if you burn peat, if you burn young coal, you emit about twice as much, 117 tons of CO2 per terajoule of energy. So not all fossil fuels are created equal. CO2 from fossil fuels is intrinsic to the process. It is an externality in the economic sense of the word, but it's essential in the chemical sense of the word. If we're talking about a problem like acid rain, that if we burn fossil fuels and there's a bit of sulfur contained in the coal or in the oil that we burn, and that gets emitted into the atmosphere, and that causes plants to die and fish to die and what have you, that is an economic externality. It's not intended an uncomplicated consequence of our economic activity, but it's also a chemical nuisance because sulfur doesn't burn. And actually, you'd rather, if you're running a power generating plant, you'd rather have fuels without sulfuring. Or if you're running a car, you'd rather have fuels without sulfuring because they corrode your engine. And so on and so forth. This is not true for CO2. What we do when we're burning fossil fuels is we take a carbohydrate, that is some sort of molecule with lots of carbon and lots of hydrogen in. We break the chemical bonds between the carbons and the hydrates by adding energy. And then we add oxygen, and then new chemical bonds form. The hydrogen goes to H2O, water vapor. The carbon goes to CO2, carbon dioxide. And it's in the formation of those new chemical bonds between the C to the O2 and the H to the H2O that we gain energy. That's where the energy comes from. That is why if you set fire to a lump of coal, you gain energy. That is why we do it, right? You cannot get energy out of the carbohydrate without producing CO2, because it's in the production of CO2 that you gain the energy, right? So it is intrinsic to the process. And that's an important thing to keep in mind. So there's no end of pipe solution there or anything, or change in composition of fuels or whatever. That just doesn't work. And another important source of carbon dioxide is land use change. Again, this is intrinsic to the process. What we have done is we replaced large trees with small grass that affect the albedo. But trees are made of carbohydrates, just like all plants. You mainly clear trees by burning them. So that emits a lot of CO2. And then what we replace forest lands with is mostly grasslands. So you put cows on so that they can eat steak and burgers, right? Grass is also a carbohydrate, but it's not smaller in volume. So the net change of replacing tall trees with small grass is then a lot of carbon. The CO2 is emitted back into the atmosphere. Cement production is the third source of CO2, much smaller, a few percent. Again, if you look at the chemical process, we start with limestone. It's too much carbon in, so we drive out the carbon, the carbon atoms by heating it, and it has to go somewhere, and it goes to CO2. You can't make cement without producing CO2. Second most important greenhouse gas is methane, CH4. CH4 goes by various names. If we put it in a pipeline and bring it to our house to cook, or bring it to a power plant to make electricity, we call it natural gas. But if that pipe is a bit leaky and the stuff gets out, the CH4 goes out, then it's in the atmosphere, and we call it methane. Chemically, it's exactly the same stuff. It just goes by a different name. And of course, if you transport natural gas at a large scale and you extract it at a large scale, then some of it gets leaked into the atmosphere. That's actually not the most important source of methane at all. Much more important is anaerobic digestion. So if you take the plant material and you let it decompose in an area with a lot of oxygen, then it goes to CO2 and H2O. If you have plant material or organic material and you let it decompose in an anaerobic environment, an environment with little oxygen, it cannot go to CO2 because there's no O, it cannot go to H2O because there's no O. So it goes to CH4, methane. That's the next preferred route of decomposition. Now, where do you have a lot of organic material and not a lot of oxygen? Landfill. You go through your bin, you shouldn't, but if you would, then you would see that there's a lot of organic material in there. A lot of it gets landfilled, that is piled into a big hole in the ground, and then they put other stuff on top. There's not a lot of oxygen around there, so it decomposes to CH4. Now you can imagine to also put a roof on that and just capture it and do useful stuff with it, like burn it to make electricity or make heat, right? There's another area where there's a lot of plant material but not a lot of oxygen. That is in wet rice fields, paddy rice. You have all the leaves of the rice plants underwater decomposing. No oxygen, so it goes to CH4. Well, you can imagine putting a roof on all the landfills, at least in Europe. You would have a harder time imagining putting a roof on all the rice fields, and it would keep the sun out, so plants won't grow. So that's perhaps not a solution. It's much harder to capture and to do something useful with it and to avoid these emissions. The alternative there, talking about emission reduction options, is to switch from wet rice to dry rice. Where you don't have this problem and it goes instead of CH4, which per molecule is about 20 times as potent for greenhouse gas as CO2. Problem with dry rice is that it's not half as productive as wet rice. So then you take an enormous hit in your food production. And a lot of people depend on rice as their staple crop. The fourth source of methane are ruminants, essentially cows, and animals like cows. Again, this is intrinsic to the production system. So what do cows do? They eat grass and they make milk. What do cattle do? They eat grass and they make meat. Milk is a carbohydrate, a bit of fat in, but a lot of carbohydrate. Meat is a carbohydrate. Grass is a carbohydrate. But if you look at the chemical composition of grass relative to the chemical composition of meat, then you would see that you would have too much hydrogen in your grass. Both are carbohydrates, but one has a lot more H than the other. So somehow in that conversion process from grass, which is indigestible to humans, to steak, which is digestible to humans, you need to get rid of hydrogen. And that is what cows do. Or cattle. Hydrogen is a very dangerous gas. So if you're a cow, you're eating grass, you need to get rid of the hydrogen. If you don't get rid of the hydrogen, if you have hydrogen in a oxygen-rich environment, you form hydrogen radicals, which sort of destroy everything. They're highly reactive, and they just take your cells apart. So you don't want to go there, fortunately. There's not a lot of oxygen in our tummies. If there's no oxygen, then H goes to H2. H2 is the stuff that floats zeppelins. So if cows were to eat a lot of grass, get rid of the hydrogen would be in their stomach, hydrogen gas would form, and they would not be cows, they would be zeppelins, they would go float up in the air. That's not how they solve this problem, right? Obviously, they're fairly down to earth. A long time ago, ruminants formed a symbiotic relationship with methogenetic bacteria. And what those bacteria do is they sacrifice one useful atom of carbon in order to get rid of 4 harmful atoms of hydrogen and make CH4. And the cows then burp out that hydrogen. You have to do that somewhere in the world. Now, in order to understand just how fundamental this is for the conversion from grass to food, or for food that is digestible to humans, we can look at an animal that occupies the same ecological niche. The kangaroo. Kangaroo also eats plant material and converts it into meat and milk. Kangaroos don't make methane, they make acetate instead. And they poop that out and then burp it out as it's a solid. Now, you probably know that there's a large distance between, in evolutionary terms, between cows and kangaroos. They're nowhere similar. So in order to make a cow that doesn't produce CH4, you need to re-engineer its metabolism so there is the metabolism of a kangaroo. That's a major task. The alternative is to give up on cow steak and eat kangaroo steak instead. If you want climate-friendly steak, you should switch to kangaroo. And of course, kangaroo should be raised locally, right? So that you don't get transport emissions. But that is how fundamental these methane emissions are to our food production system, right? It's rice and it's meat, and it's very hard to imagine to do this at a large scale without emitting large amounts of methane. Nitrous oxide also comes out of agriculture, essentially comes out of over-fertilization of agriculture. It's very hard to convince farmers when their output is at stake to use less fertilizers. So tend to be very, very cheap. That is where the nitrous comes from. And then the other gases, so small in volume but very, very potent in terms of their warming effect. They are mostly specialized industry, very specialized applications, coolants, refrigerants, foams and those sort of things, semiconductors, and what have you. These gases typically come out of a very specific industrial process. And there's typically a small number of large sources. Whereas for the other sources of greenhouse gases, we're talking about a large number of small sources. Right? This is important for climate policy that we'll be talking about tomorrow. So that is where the stuff comes from. I promised to talk about scenarios, but I'm still not there, right? What we're looking at here in black are the global total CO2 emissions from fossil fuel combustion over the last 40 years. And what you see, and it's all indexed out of 1971, what you see is that over that 40-year period, CO2 emissions from fossil fuel combustion have doubled. So it's gone from 1 to 2 units, something matter. And then the question, before you start sort of like thinking about what would future emissions be, it makes sense to ask yourself, so how come they doubled, right? And one way of looking at this is to use the so-called Kaya identity after Yuichi Kaya of Tokyo University. And the Kaya identity is given at the top. And it's an identity. What it says is that emissions E equal the number of people P times per capita income Y over P times the energy intensity of the economy X over Y times the carbon intensity of the energy sector E over X. You cannot argue with this identity. It is an identity. P cancels against P, Y against Y, X against X. And what we have is E equals E. And that is true, right? It's nonetheless useful as a way of thinking about where do our emissions really come from. So what we see in this graph is that global CO2 emissions have doubled over the 40-year period. In blue, we're looking at the increase in the world population, which over this period was about 80%. So emissions grew by 100%, population grew by 80%. So emissions per capita grew by about 20%. Income or output per person also grew by about 80% over this period, which then means that the economy grew by 80% plus 80%, around the times, about 170%, whereas emissions only grew by 100%. Right? So emission growth has been slower than economic growth. And that is something that immediately follows from a decomposition cycle. Why did it go slower? Those are the two other lines that are there. In orange, you're looking at the change in energy intensity or the improvement in energy efficiency. Energy efficiency is how much energy you use to generate €1 of value added. That's the definition of energy intensity, and if that goes down, then energy efficiency is reciprocal, improves. And what you've seen is that over the last 40 years, there's been a steady improvement in energy efficiency of about 30% over the 40-year period. So that's 0.7% or so per year. And then the final part of the KI identity is carbon efficiency. Much less action, that's the green line that you're looking at. About 10% over the 40-year period that we have shifted away from, mostly from fossil fuels that emit a lot of carbon dioxide, namely coal, to fossil fuels that emit much less, namely gas. Most of the trend that you would see in the period up to 2000 is indeed from a shift away from coal towards gas, started by this figure that is reviled by the environmental movement called Maggie Thatcher, kicked it all off. And then after 2000 you see a reversal in this process where mostly due to the growth of the economies of India and China, which are heavily fueled by coal, because that is a local resource. And then if you start adding up all these trends, you indeed get to the 80% growth over the 40-year period. Now, knowing where our past emissions have come from, we can now start thinking about where will our emissions be going. And I've showed you this picture already. This is exactly what is behind the alternative colored lines that are here. Different assumptions about population growth, economic growth, energy use, and energy supply. Right? So if we want to know what will the climate be like in the year 2100, then we also need to know what will our greenhouse gas emissions be between now and the year 2100. And if we take the Kaya identity again as a way of thinking about it, it means that we need to know how many people there will be, how rich these people will be, how much energy they use, and what sort of energy they use. And then we have done CO2 from fossil fuel combustion. And then we need to do the same for how many people there will be, how rich they will be, how much meat they will eat, what sort of meat they will eat, and so on and so forth for all the different sources. And you can imagine that this is quite a large task, and it's quite a difficult one. Because for starters, we don't know how many people there are on the planet. right? Today. There's websites out there that will give you the number of people on the planet now to 9 significant digits. They lie, right? I don't know how many people there are in the Netherlands at the moment. The best population registration system in the world. Well, the Swedes and the Norwegians probably. But we don't know how many illegal people there are, right? Because we don't really know how to count them. You go next door to Germany, they do know how many people there are because they have a pretty good population registry system. But because of World War II and what they did, we actually cannot look into those records. And our eastern neighbors do is count the number of people every 10 years, and in between there's guesswork, right? If we go to a country like Nigeria, do you really think that the population of Nigeria knows how many people there are in Nigeria? Most Nigerians don't fill out the birth certificate or don't have the birth certificate filled out when they get born. This is the basic guesswork. There's large parts of countries like Nigeria that are completely beyond government control. So how would the official statisticians know how many people there are? If they would visit the area, they would get shot at, right? So for starters, we don't know the base situation. We don't know what is going on in the year 2015 for the simplest of these all population. But what we need to do is somehow project into the future how many people there will be. We also need to project economic growth over a 100-year period. Models are good at some things, they're not so good at other things. Most people would say that we're not quite up to this task yet. And the same is true for projections of energy use and so on and so forth. So this is a rather difficult task. It is a necessary task. A lot of the work that you see in climate change and in climate policy is driven by people who are either brave or stupid enough to build these long-term scenarios. And here we're looking at some of the results. Again, we're following the Chi identity. Top right, looking at projections of population. Top left, population, top right, per capita income, bottom left, energy intensity, bottom right, carbon intensity. The colored lines are sort of the average across models, the areas that you sort of like vaguely see around it, the range between the models. Give you a further idea of the uncertainty about this all. So 5 years ago, 6 years ago, when these pictures, or the data behind these pictures, was generated, the orange line population was the World Bank's best estimate of the future population, and essentially said population is going to grow from the current, 7-8 billion to 9, and then it's going to start falling. That was 5 years ago, and it actually gave a very narrow range of confidence around it. 5 years later, they changed their minds and said, no, the blue line is more like one. The difference is a population peaking at 9 billion around the year 2040, 2050, versus 14 billion in the year 2100, and no end to population growth in sight. The difference between these two scenarios is fertility in Africa. So between the year 1990 roughly and the year 2000 roughly, fertility dropped very rapidly in Africa, and a lot of the demographers got very excited and sort of assumed that Africa had found a new demographic transition and assumed that this 10-year trend would continue forever. after 2005 or so, African mothers have returned to form and gone back to the much longer trend. Fertility is coming down. It's coming down, but not nearly as fast as during that last decade of the previous millennium. And the difference is 5 billion people on the planet, but those 5 billion are 5 billion Africans. So that's population. Economic growth, you see at top right. These are scenarios that were produced by the Intergovernmental Panel on Climate Change. The IPCC, as it's known, is an agency of the United Nations. So that means that whenever it produces something, all countries have to give their consent, essentially. And so it's no small wonder that essentially what's the range of possible futures that you see here depicted is that either we all grow rich or we all grow very rich. So they basically followed the optimistic assumptions that politicians tend to make about how their economy will fare, and they added it all up, and that's what you see depicted here. So all these scenarios assume rapid economic growth everywhere and more rapid growth in poorer countries than in richer countries. So a lot of income conversions over time. Well, what you see happening in these graphs is that in the most pessimistic scenario, so we're currently at around 1, and the year 2100 we're around 4. That's the most pessimistic. But the world average income is around $7,000 per person per year. That will go up to 4 times 7 is $28,000 per person per year in the most pessimistic scenario. So that's Portugal now, right? We would hope that it is, right? But none of these scenarios allows for the sort of secular stagnation that we've seen in large parts of Africa. That magically disappears in these models. Then bottom left, we're looking at the projections of energy intensity. In black, you're looking at the trends of the last 40 years. It went up first, then it went down, and then it went up a bit. The scenarios only allow it to go down and down and down further. And the discrepancy between the historical record, again in black, and projection is even clearer for the carbon intensity of the energy system. That's the bottom right, where you see that the first decade of observation is a very rapid decline, rapid switch from coal to gas, then a less rapid decline, followed by 2 decades of moderate increase. In the projections, there's almost only room for a further move away from carbon-intensive fuels towards carbon-extensive fuels. So whenever you're looking at these scenarios that people have used to derive future climate change and make assumptions about how warm the planet will get and how much we should be doing about it, and what it would cost to do something about it, it's good to keep this in mind. Because all of this derives from a set of assumptions. Some of which are more credible than others, but a set of assumptions that feeds into these exercises do not span the range of possibilities in any way, or do not even necessarily conform to our best guess of what has happened in the past, right? So that is something to keep in mind. But I started all this by saying that this is hideously complex, right? There's so many things involved when you project over such so long period. So it's much easier to complain about what they've done than to replace it by something that is perhaps more sensible. Final slide, not necessarily the easiest. In all this story, what matters a lot is what fuel do we burn? And therefore, we also need to have a close look at what fuels do we have. And that is shown on this slide. So on the vertical axis, we're looking at the various forms of fossil fuels, 2 gaseous ones at the top, then 4 liquid ones in the middle, those are the oils, and then 3 solid ones at the bottom. And then in the colors, we're looking at various gradations of certainty. So in black, we're looking at the reserves. So reserves, or a reserve of a fossil fuel, say of oil, is that oil that we know is in the ground, we know where it is, we know how to get it out, and we know how we can get it out, that we can get it out profitably at current costs and current prices. That is the definition of a reserve. And then there's also resources, stuff that we know is in the ground, but we can't get out with current technology, but we think we might get out with future technology, stuff that we suspect is out there, but we haven't really bothered looking. So there's a gradation of resources, and the gradation of resources that is used here is proof, probable, possible. And the less likely they become, the lighter the color, not necessarily proportional to the likelihood. And then the third bit of information is how big are these? And the units that are used is parts per million by volume. And the thought experiment is we take all the oil reserves that there are and burn them in one go, and how much CO2 would we then have added to the atmosphere? Now, that's physically impossible to do so. It's also rather unwise to do so, because we also suck out a lot of oxygen and we would generate a lot of heat, so we don't want to do this and we can't do it. But the thought experiment, what is if we burn all this stuff in one go, how much CO2 would we add to the atmosphere? To give you an idea of the scale of this, the policy debates is about limiting carbon dioxide or greenhouse gas concentrations to around 450 CO2 equivalent. It stands now at around 380, perhaps 400 if we add the other gases. So the policy debate is sort of like in the order of 50 ppm. That's the most optimistic ones. There's also debate where we should go from 450 or 550, so that is 100 parts per million by volume, right? So the policy debate is really about, can we burn another 100 parts per million, or can we burn another 200 parts per million, right? So the horizontal scale is indeed the policy relevant scale. So now what does this graph tell us? Well, if you take the conventional oil and gas, the current mainstays of the world economy, there's natural gas and crude oil, and we add up the two, then we find about 100 ppm. So that means that we can burn all the oil in Saudi Arabia and Kuwait, and burn all the gas in Qatar and Russia, and stay within what most politicians would say is a reasonable thing to do, without causing a lot of climate change. So that then implies two things. One, actually beginning to run out of conventional oil and gas. Important for the way we think about the problem. But also, conventional oil and gas is not the problem at all, because we can burn all that stuff and stay within safe limits. Or limits that are deemed to be safe. It changes the political tone of the debate completely, right? Because conventional oil and gas, that's Saudi and Kuwait, that's Russia and Qatar, that's ExxonMobil and Shell and BP. So those companies that are constantly vilified by the environmental movement. The countries that are constantly vilified by the environmental movement. It's not the climate problem at all. Right? The climate problem is driven by what will replace conventional oil and gas when it runs out. When it runs out, will run out within my lifetime. It's not within your lifetime, but not soon. And that's an important thing to keep in mind. Of course, if we opt to switch to renewables instead of unconventional oil and gas, then the climate problem disappears by and large, right? If instead we opt to move, as the market seems to be doing at the moment, to unconventional oil and gas, mainly shale, then we would have a climate problem. If, as a third option, we decide to move back to coal as the mainstay of our energy system, then we have a large climate problem. And if you start adding up the coal bars, you see that we can really, really make this place very, very, very hot. Right? So a lot of the future of the climate system is driven by the question, not the question, are we running out of conventional oil and gas? Because we are, but by the question, what will replace conventional oil and gas? And that should also, much more than it actually does, shape the debate about climate policy. We'll be coming back to climate policy in the third week, so I'll probably return to this figure. For now, I'm going to stop here. It's out tomorrow. Tomorrow I'm going to talk about the options for emission reduction, the costs of emission reduction, and policy instruments for emission reduction. Okay, I hope to see you guys then.